Okay, this video here is about exponential functions, and with exponential functions they're what we call to the power of functions, to the power of x, such as that, and they can have any base. So for example here, I've got the base 2 there, but they can have base 10, base 20, base 100, but the most common ones we use in our course are base e exponential functions. So we'll get to those in a moment. But here's the basic structure of an exponential function, and we'll go through some characteristics of them in a moment. But number one thing you'll notice is that the x-axis, the y-intercept is always, unless you've moved the graph somewhere or dilated it, whatever, is 0, 1. And why is that the case? Because if you look at y equals 2 to the power of x, for example, if x is 0, anything to the power of 0 equals 1. So it wouldn't matter what our base was, it could be 10 or 20. If x is 0, we're always going to get 1. So these exponential graphs, as I said, unless they've been dilated or moved, pass through that point 0, 1, because when x is 0, y is 1. The other point in this graph, you'll see it here, is 2, 4. That's because if x is 2, we get y equals 2 squared equals 4. So pretty obvious there how we got 2, 4. Alright, that's about all I'll say about this graph for the moment. We'll move on now to y equals 10 to the power of x, just as a contrast. And you can see once again, it's passing through that same point there, 0, 1. Another point we've drawn here is 1, 10. Why? Because if x equals 1, we get 10 to the power of 1 equals 10, y equals 10. So you can see the larger the base there, the steeper that incline is there on the graph. If you compare that to the previous graph, the gradient is quite different to that graph. Y equals 10 to the power of x. There's a steeper gradient there. Alright, third one, and I haven't written this down, but this is y equals e to the power of x, and as I said, this is the most common exponential function we use in this course. Can't rule out other bases, but e to the power of x is pretty important. So once again, if x was 0, you get e to the power of 0, y would equal 1, so you get that point there, 0, 1. If x was 1, okay, you get y equals e to the power of 1, which is just e. Hence, you can see I've got the point there, 1, e, and there's my other point, 0, 1. Similar sort of shape again as the previous two graphs I showed you. So there they are, 2 to the power of x, 10 to the power of x, and e to the power of x is that one there. If you want to stop at this stage and get some notes around those three graphs, feel free. Features common to those exponential functions: they all cross the y-axis at the point 0, 1. I've just pointed that out because anything to the power of 0 is always 1. They don't dip into the negative, okay, because there's no x value that we can put there in any of these graphs, whether it be 10 to the x or 2 to the x or e to the x. There's no x value that's going to give us a y value of a negative number. Okay, so we're never going to get a negative y value unless later on, as you'll see, the shifts and reflections, etc. The horizontal asymptote will be there at y equals 0. Okay, it won't dip below that. The domain is always real numbers. Okay, I've stopped these graphs over here, but in reality they keep on going. Oops. They keep on going, okay, this way and this way. So they'll eventually cover all x values. So the domain will be real numbers. The range is positive real numbers because of that asymptote there at y equals 0. That means the graph never goes below, but it will still cover all real values for y. And they're all increasing functions in their purest form. So if I was to draw a tangent here to that line at any place along that curve, okay, I'm going to get positive gradients all through. Okay, so positive gradients everywhere, so it's always an increasing function. Okay, so there's some characteristics of exponential functions. Once again, you can pause here at this stage and get those down if you wish. Alright, time to look at all our dilations and translations and reflections, etc. Let's start with dilations from the x-axis, that is taking the graph further away from the x-axis. So I've drawn 4 graphs here. So the first one I'll point out is the standard graph, this brown graph here, which is y equals e to the power of x. Next one I'll point out is the blue graph, okay, which is y equals 3 times e to the power of x, sometimes written as just y equals 3 e to the power of x. The times multiplication sign is not always there. And that's the blue graph, and if you contrast the brown and the blue graph, you can see, might just pick another colour here. Let me see, let's go with that colour. You can see that if you compare the brown to the blue, there's been a dilation, perhaps the arrow go the other way, there's been a dilation from the x-axis by a factor of 3. So that 0.10 is now 30, and any other point on the graph that I chose would be dilated 3 times. Okay, so that point there, just here, is 1, e. So on the blue graph, okay, it would be 1, 3e, 3 times from the x-axis. With the green graph, it's 4 times e to the power of x, or probably more commonly written as y equals 4e to the power of x. It's a dilation by a factor of 4 from the x-axis. So that intercept of 1 is now an intercept of 4, and so on. So dilation by a factor of 4. The purple graph is a half e to the power of x, probably more commonly written as y equals e to the power of x on 2. Remember, they're the same thing. And you can see with that one, we've got a dilation by a factor of a half from the x-axis. So instead of the intercept being 1, 0, it's a half 0. And any other point, there's a relation by a factor of a half towards the x-axis. So in effect, those dilation factors of like a half there, or a third, etc., bring the graph closer to the x-axis. Whole number dilations like 3 and like 4, they take the graph further away from the x-axis. Alright. Table on page 164, if you'd like to turn to that now, if you've got your textbook with you, is a really good one, because it shows you, and that's an exam type question by the way, that table there, it shows you the effects of the dilation. Okay, the y-intercept, the domain stays the same, you notice there, on all those graphs the domain is still real numbers. The range hasn't changed either, that's positive real numbers. The horizontal asymptote hasn't changed. The dilation factor has from the x-axis, so that's important to see. So in effect there, if we just take the y equals 3e to the x graph, so this one here, okay, what we've got is say an original point x comma y, and now it becomes x comma 3y. Okay, so the y value is multiplied by 3. Our original y value there was 1, and then it becomes 3. Okay. Next up, we've got dilations from the y-axis. So dilations from the x-axis are controlled by a coefficient there in front of the e to the power of x, or the 2 to the power of x, whatever it is. But the dilations from the y-axis are controlled by the coefficient of the x itself. Okay. And here we've got to think a little bit differently. Let's look at that red graph first of all, y equals e to the power of 2x. Now you notice with all these graphs I'm about to show you that the x-intercept stays the same. Okay, that's because if x is 0, if we take y equals e to the power of 2x for an example here, okay, if x is 0, 2 times 0 is still 0, so it's going to be 1. Okay, so regardless of the number in front of the x, if x is 0, we're going to get power of 0, which is 1. It won't be affected. Okay, what will be affected are some of the other points. And you'll notice here the black graph this time is the original y equals e to the power of x graph. some of those others. That's the black graph there. And the e to the power of 2x graph is the red one, and you'll notice that point there, which is 1e, is now a half e. Okay, so it's been dilated by a factor of a half towards the y-axis. So it's halfway from the original point to the y-axis. Now our coefficient there is 2, and we've got a dilation of a half. So what we can say here is that the graph is dilated by a factor of, now if our general form is y equals e to the power of kx, okay, that's our general form, it's dilated by a factor of 1 over k, because remember 2 there is dilated by a factor of a half from y-axis. Okay, so dilated by a factor of 1 over k. So if we had e equals 3x, it would be dilated by a factor of a third. Okay, the point that we're looking at there would be 1/3 e. Okay, so if we've got a coefficient like we have here, if I just change my colour to red here, if we've got a coefficient there of a half, and we're dilating by a factor of 1 over a half, we're actually dilating by a factor of 2, and you can see that's happened here. Okay, with e equals x over 2, the blue graph, we've gone further away. We've been dilated by a factor of 2 from the y-axis. Okay, so once again, 1 over the coefficient, 1 over a half is 2. Table on page 165, at the bottom, I should say, because there's 2 tables there. So at the bottom of page 265. Explains that quite nicely. The effect there of the dilations from the y-axis. Okay, and once again, just pointing out the x-intercept doesn't change. Okay, it's still there, regardless of the coefficient in front of the x. The domain is still real numbers. The range hasn't changed. And we just talked about the dilation factor there as well. Okay, so here, if our original point is xy, okay, if we've got a 2 in front of the x there, our point now becomes x and a half. Sorry, not x and a half y, got that wrong myself. It becomes the same y, okay, the y hasn't changed, but x would be a half, okay, or halved, half of x. And you can see that happened here. Okay, we had 1 comma e, okay, so the y hasn't changed, but what changes, the x was halved. Let's have a look at the table on page 165. It explains it really well. Alright, more translations now. Vertical translations. Now, some of these follow a familiar pattern to what we're used to. Okay, we're used to a situation if we've got a +1 out by itself, like that, it will shift the graph up 1 place. But what, of course, that means is if we do that, our asymptote changes from y equals 0 to y equals 1. And all other points on our graph shift up 1 unit. You can see that's happened there, and it's also happened here, here as well. Okay, those points have shifted up 1 unit. So, cut a long story short, it shifts the graph up by 1 unit. But be careful, what I've drawn there is, what I've written there, sorry, is not, the +1's not attracted to the x, attached to the x, it's out separate. So be careful, because it can get confused with that. It's clearly a +1 to the e to the power of x. Moving on now to horizontal translation, and here, if we've got a plus or minus attached to the x like so, e to the power of x minus 1, we get a translation. And it's the same as what we looked at earlier in the year, guys, with a -1 takes it to the right, and a +1 takes it to the left. Okay? So here, I've just changed it because I realised I made a mistake. Those with a keen eye. I've got y equals e to the power of x plus 1. So that will take the graph 1 place to the left. So in the black here, I've got y equals e to the power of x. There it is there. Okay. And I've shifted that because of the x plus 1 situation. I've shifted it one place to the left. So to there and to there. Okay, and all other points will be shifted one unit to the left. And that will give me my new graph of y equals e to the power of x plus 1. So that's the horizontal translation. Domain and range don't change. Asymptote doesn't change when you're just doing that simple translation, horizontal translation. Okay, this one's a reflection in the x-axis. So if the negative is out the front of the e to the power of x, as it is in this case, right? So there we go. Negative e to the power of x as opposed to e to the power of x, which is there. It simply gets reflected, okay, in the x-axis. Oops, I've already written that down. So reflected in the x-axis. We've done those reflections before, so I won't dwell on them, but the points above the axis are reflected below the axis. The x-axis, that is. The other reflection is a reflection in the y-axis, and this is when the negative is out the front of the x here in the index. We get a reflection in the y-axis. Okay, so e to the power of negative x is the red graph, e to the power of x is the black graph, and you can see the reflection there. Finally, just be careful with a graph such as this. If we've got y equals e to the power of 2x minus 1, we've actually got to factorise the index there. So it's going to be 2 outside of x minus a half, like so. That then gives us two things. That 2 there means that we've got a dilation by a factor of, remember it's 1 over 2 from y-axis. Okay, and that negative a half means we've got a translation 1 on 2 units to the right. So just be careful with those ones. Sometimes a temptation just to say it's a translation of plus 1, but you've got to factorise it first. Okay, that's background now on exponential functions. The next video will actually do some problems associated with them.